The analysis of this effect, because we're talking about transfer of energy and momentum, comes down to a classic collision type of analysis. So this will be our collision analysis of the Compton effect. And of course, as in any good collision analysis, there's a before, there's a before and an after. In the before, what we're talking about is we have our incoming photon. It has an energy E equals h nu. Now, something very important I want to point out as we carry out our analysis. When I had originally described the experiment, I made the incoming frequency nu sub naught. In this case, so it was nu sub naught, but we're going to be doing a lot of algebra coming up, so I'm going to be dropping the naught on the nu. So the idea is the incoming photon will have frequency nu. And then it has, of course, by our hypothesis, a precise amount of momentum determined by our classical limiting analysis of the classical electromagnetic field, which always has momentum in direct proportion to energy, but momentum would be the energy over c. And then, of course, we have our electron, which is just sitting there. Its momentum we're going to take to be 0. Of course, it actually might be whizzing around inside some kind of an atom, but the energy of that whizzing around is at most on the order of kilovolts, whereas these incoming gamma rays can be megavolts or even higher. So the momentum, to a very good approximation, is basically 0. Likewise, when we look at the energy that this electron has, it's going to be the energy associated with an essentially 0 momentum. But the thing we need to keep in mind is that the rest mass of the electron is some 511,000 electron volts. But we are having a collision here with something with multiple millions of electron volts. And so the recoil of this electron is going to be relativistic, or very well could be. So we had better account for relativity. And in relativity, the energy of a resting particle is, of course, the famous mc squared, where this m then will be the rest mass of the electron. I'll put a little dashed m sub e just to remind us this once, but I will just be writing m throughout the rest of this analysis. So that's before the collision. After the collision, we have two things going on. First, we have our photon now that is going up into our detector, right? And it has scattered up now at an angle theta because we have placed our detector up here and we're only looking at radiation coming off at an angle theta. The energy of this outgoing photon then will be h times the new frequency, which we will call nu prime. That's the frequency after the collision. And we're hoping that this nu prime will reproduce that second peak that we saw in the Compton scattering. This photon, of course, is also carrying a momentum. And again, our current hypothesis is that is exactly its energy divided by the speed of light, c. Now, we also have the electron, right? It's going to be recoiling probably somehow in a downward direction because we have to balance up and down momentum because there was no vertical momentum at the beginning. So I'll sketch it, maybe it looks something like this. And that electron then is carrying off some momentum p, and that momentum for us is unknown, and then it will have an energy E given by the relativistic kinetic energy formula, which when you are not just at rest, isn't just purely mc squared, but root mc squared squared plus the speed of light times the momentum quantity squared. So if we look at this before and after, we know the drill. We're going to say the momentum before is the same. Then we're going to say that the energy before is the same as the total momentum after, adding them as vectors. We're then going to do the same thing with the total energy before and the total energy afterwards. And if we think a little bit about our algebra, we have mostly fundamental constants in here, m and c and Planck's constant h. The variables that we have are nu, which is not an unknown, right? Nu is the incoming photon frequency. Nu prime is, in some sense, an unknown, but that's what we're going to be trying to solve for. There's only one other unknown variable in here, and that is this recoil, the magnitude of this recoil momentum of my electron, right? Because I also know the outgoing angle theta. So there's really only one extra unknown, and our job will be to eliminate this extra unknown, the momentum, the magnitude of the momentum of this electron. And once we eliminate that, we will have an equation that can tell us the new frequency that we hope to figure out, this frequency that we're measuring in our detector, in terms of the incoming frequency of the incoming gamma rays, and then, of course, all these other fundamental constants. So that's the basic structure of what we're going to do. It's just now a matter of sitting down and doing it. It does involve, I'll warn you, there's going to be quite a bit of algebra coming up, but I hope to, while we're going through it, to exhibit some good algebra habits. Also, I really want you guys to get and understand everything that we do, and so I don't want to just pop the final answer out at you. I want you to really see where this comes from and what this type of an analysis involves. Okay, so we're going to do a before and after analysis. Let's begin with energy. Energy is always a little simpler. It helps to get us warmed up in a theoretical analysis to begin with the simpler thing. And of course, it's simpler because it's a scalar. So let's look at conservation then of energy. And we have to set the before energy, which is the energy of the incoming photon, h nu, plus the energy of the essentially at rest electron, mc squared. And that will have to, of course, equal the total energy afterward, which has the energy of the outgoing photon that's been scattered at angle theta, plus then the energy of that outgoing electron, which is root mc squared, which is just, of course, some known constant, plus then again c times p quantity squared, right? And that has my one extra unknown in it, p, that we hope to solve for. Now, the next thing we could do is write down the equation that goes for conservation of momentum, right? And then start massaging the equations. But just to stay organized, since we've been down these kinds of roads before, we know how it goes if we want to try to eliminate this momentum, right? The trick is going to be to solve for it in both the energy equation and the momentum equation, and then to set those two things equal so we can eliminate that unknown. So let's solve for the momentum p, or something closely related to it. Now, to get at that momentum p from here, you see I'm going to have to undo this square root, and the way I do that is I subtract h nu from both sides of my equation and then square it. So I'll have h nu minus h nu prime plus mc squared. This will be then equal to just the square root, but then I square both sides of my equation, so then this thing here will become squared, and then on the right hand side I have the inside of the square root, mc squared squared plus cp quantity squared. Now, next, you guys know the drill. You know how to square something like this. You get the squares of each of the terms inside here, plus then twice all of the different cross terms. And something very interesting is going to happen when I put down the squares of each of these terms. One of the terms will be mc squared squared, which is exactly what I have on the other side of the equation. So those two terms will cancel, and I'll just be left then with cp squared alone by itself. And that's a great thing, having this cp squared, right? Because then it's easy to get at p, so I can eliminate it in my remaining equations. So that's going to then equal what is left when I expand this quadratic, every single term, except, of course, I can skip writing the mc squared squared term, because that canceled from this side of the equation. So what would I have then? Then I would have the h nu term squared. I would have the other energy term squared, h nu prime squared. Again, I can skip the mc squared squared because that will cancel this one. I then have my cross terms, and there's really two types of cross terms. There's the quadratic type that has two different nu's in it as products. So I'll have minus 2h nu prime. That's one of my cross terms. Then there's two other cross terms. I'll have 2h nu mc squared minus 2h nu prime mc squared. Now, those two terms have many common factors, so let's factor those out. They both have a 2 in front, so I'll keep that 2. They both have an h in front, so I will keep that h. One has a nu and one has a minus nu prime, so that's where I get my 2 factors. And of course, both of them multiply mc squared. So you can see I have my terms. I've got 2h nu mc squared, which would be this cross term, and then minus 2h nu prime mc squared, which of course would be this cross term. Beautiful. So I like this equation. This is, maybe we'll call this equation A. I've got my unknown, isolated the one I want to eliminate. And that's what we learned from conservation of energy. Now, conservation of momentum, right, is going to be a little bit more complicated because this is a vector. But we can do this in a vector diagram, right? The total incoming momentum is this vector here, right? And the total momentum at the end is this upward vector of my scattered photon and this downward vector of my electron's momentum. And the sum of these two vectors, head to tail, right, would have to match this one. And I can add these head to tail by parallel transporting this momentum vector. It will have to end up, looking something along the lines of that triangle there, right? When I move this momentum up to here. So let's sketch that out then carefully and put some numbers on things. So the horizontal piece was the horizontal incoming momentum h nu over c. My scattered photon, so that's before, and then that has to be equal to the sum of this vector, which is my up electron momentum, right? The one that I've detected at frequency nu prime. So it would have this momentum directed upward at angle theta, because that's where I've placed my detector. And finally, what I have to add to this vector, head to tail, to equal the original piece, must be that electron momentum p. Great. So now, again, our job is to solve for this p so that we can equate it to what we have up here and then eliminate our only unwanted unknown in the equation. Now, to solve for p, you can see we've got a triangle. It's going to be some kind of trigonometry. It's not necessarily a right triangle, but we have the advantage that we know the angle theta opposite to our unknown side, right? So if it were a right triangle, this would be easy. P would be the hypotenuse. It's not quite a right triangle, but that just means we should be using the law of cosines. So let's apply law of cosines to this. And now, for law of cosines, what that will tell me is this squared will equal the sum of these two squared, right, minus twice their product times cosine theta. Now, before we do that, notice it's going to give us p squared. And p squared is almost exactly what I want. Actually, if you think about it, what I would really love to have would be cp squared. So I could line up perfectly with this upper equation, just to make our lives easier. But that's easy enough to do, right? This is a triangle with an angle theta. But by similar triangles, if I get the same angle, if I just scale up all of my sides by some constant factor. So let's multiply every side by c. Multiply this by c, this by c, and this by c. Then my c's will cancel, you see? And now I can directly apply my law of cosines. And that says that this side, which is cp squared, kind of like a right triangle, will be the sum of the squares of these other sides. So we'll have an h nu squared and an h nu prime squared. And then, though, because this is not a right angle theta, it's minus twice the product of the lengths of those sides. One is h nu, one is h nu prime, times the cosine of the angle that is opposite to the side I'm solving for. So that's what law of cosine tells me. And this is beautiful too now, right? Because notice this equation, which I guess I'll call equation B, right, is lined up perfectly. This equals cp squared. These terms also equal cp squared, so I can eliminate them by simply equating what I have in these square brackets to what I have in these square brackets. Now, I could write all that down again, but we can just kind of do this mentally. Notice when I equate those, I've got terms on both sides of the equation that are exactly equal. So this h nu squared term, squared, right, we'll cancel that one. This h nu prime squared term here will cancel this one. So I'm just left now with a bunch of terms that have 2's in them. That's kind of nice. The other thing is, again, you'll notice there are two types of term. One term has a product of two new's in it, new and new prime, like these do. And the other one has the difference of new and new prime. So that's probably a good way to group things and organize them. So I'm going to take the new prime term from this side of my equation, and I'm going to move it over to this side of my equation. So that's all that's left on my left-hand side is 2h new minus new prime mc squared. And what that will equal then is what's on this side of the equation when I also include moving this one over. Now notice, they both have the constant factor 2h new prime, right? And I have exactly one of those terms with a positive sign when I move it to this side of the equation. So I'll open a parentheses 1. And the only other remaining piece was this piece, right? I wrote this one down. I've moved this to the other side of my equation. This is my last remaining piece that I can reproduce with minus cosine of theta. And then, of course, all the other terms have canceled out. I've accounted for everything. So now it's getting down to be home stretch time, right? I just have to simplify the expression that I have here. First, easy simplification is we have common factors on both sides. There's a 2h here and a 2h here. Now, the next thing is going to be a little bit more subtle, right? What I want to do, of course, is to get all the variables that I'm trying to understand, this new and new prime, right, onto one side of my equation. So I want to divide both sides by new prime, and then get all of the constants onto the other side of the equation. So let's indicate that. If I divide by new times new prime here, I can divide this term here by new prime, right? And what's nice about that is this new cancels this new prime cancels this new prime, and the only thing really that's left, notice, I'll just underline it, is that h. Now, on the other side of the equation, something very interesting happens here. If I look at these new terms, you'll notice if I do new divided by new times new prime, that leaves me just with a 1 over new prime because the new's cancel. And then my new prime over that gives me just a 1 over new. And what's interesting to me is this mc squared here, because if I have one factor of c, c over new is something that I recognize, right? So c over new, sorry about that technical difficulty. Let me get some power going in here. C over nu is something I definitely know. You should remember that the speed of light, c, which is measured in meters per second, is the product of lambda, which is in meters, times frequency, nu, where lambda is the wavelength of the light. So I can take one of these factors of c divided by nu or nu prime, and that will give me the corresponding wavelength. So I'd like to keep, in fact, one factor of c on this side of the equation, so I'll keep that one c here. And then what this will have to equal is I have to take the m and the other c down to the bottom of the other side of the equation. This will give me h over then mc. That's multiplying 1 minus cosine of theta. That's starting to look nice and simplified. Next, as I just was saying, c over nu prime would be lambda prime. So I can get the wavelength of the outgoing light, and of course, outgoing because it's prime. And of course, once I have that wavelength, I can easily figure out its frequency. So that's just as good as solving for nu prime, right? Minus, and then c over nu will just give me the wavelength of the incoming light, which is something I certainly know because I knew its frequency. And then, what I have on the right-hand side is just this combination of fundamental constants, and that combination is usually given a name. It's usually called just lambda naught, so let's write it that way. It's some constant, lambda naught, at times 1 minus the cosine of theta. So this gives us a perfect way to find the frequency of the outgoing light, right? I know theta. This lambda naught's a constant. We'll talk about that constant in a minute. It has some very interesting features, right? And then I just take that, I can add it to my incoming wavelength, and bam, I've got my outgoing wavelength from which I can then get my outgoing frequency. So this relation here is very famous. This is called the Compton shift because it gives a very simple formula for actually the change in the wavelength. If you want, you can, instead of writing it as a shift or a change, you can just get the final lambda prime as the incoming lambda plus this amount, which, by the way, notice has to be positive because cosine is always less than, well, or equal to 1. It's always positive or 0, right? So the wavelength, the new wavelength, is always going to be longer than the old wavelength, which actually, as you'll see later, makes a lot of sense. And then, of course, if you want really the final new prime would be c over lambda prime. So we've really solved the problem in terms of predicting that new wavelength. The last comment here that I really should make here, or really should make, is the value of lambda naught. So note, lambda naught, which is called the Compton wavelength, because it's constant regardless of the incoming frequencies, right? It's just like the amount that you add to the incoming wavelength. It has units, of course, of wavelength, or angstroms. So lambda naught has a value of h over mc. Now, to put a numerical value on this, there's a cute little trick. Lots of times it's handy to carry around in your head certain combinations of fundamental constants that you know handy numerical values for. And one of those actually is h times c, which, as you can see, will come up a lot when you think about photons because they travel at the speed of light and they Planck's constant's involved. So if I multiply by c on top, I multiply by c on the bottom. Now, h times c has a value useful to carry around in your head. It's about 12,000 electron volts times angstroms. It has units of energy times distance, and then that's being divided by mc squared is the rest mass of the electron, which is 511,000 electron volts. The electron volts cancel, so you can see I will get an answer in angstroms. The thousands cancel, and I've got 12 over 500, call it about 10 over 50, which is, 10 over 500, which is about 1 over 50, and 1 over 50 is about 0.02. So it's 0.02 angstroms. So that summarizes then our analysis of the Compton process. What we can think about now are some of the consequences of that process.